Hi, so what I want to do in these short videos is explain some aspects of seminal cryptographic papers. The reason I want to do this is because I think to get the foundation of cryptography, you could always go to books. Books are very common and readily available. And then you go into papers, right? And there are many papers written in various fields of cryptography. However, there are some seminal papers that I think are foundational. Everybody would need to understand them. And sometimes you get stuck at a particular section, or there's a concept that is not explained anywhere. And I thought it'd be really good to, like in each and every video, I would focus on one paper and maybe on one aspect of the paper, one section of the paper. So the first video, I chose a very seminal paper. This is actually the original RSA paper written back in 1976. And that is the paper, that's how it looks like, written by the, big three, if you will, Rivest, Shamir, and Adelman. And the name of the paper, if you want to look it up, a method for obtaining digital signatures and public key crypto systems. Now, the first half of the paper is really easy to understand. You can just read through it. I think the first section that you would encounter that might be a bit of a challenge, especially from a mathematical perspective, is section number 6. And in section number 6, basically, you're going to encounter the main proof for RSA. That is basically to prove mathematically the correctness of RSA. When we say correctness, it usually means that I'm able to get the original plain text or message from decrypting the encryption. All right, so this is really, I think, the core of the paper. And later there are also some interesting sections we can maybe do in other videos. So what we want to do today is basically prove that if I decrypt an encrypted message using RSA, I'm able to get the original message. Now, in order to do that, in order to establish the proof, first and foremost, we have to rely on a really important theorem in number theory, and that is Euler's theorem. Now, you can also do the proof using Fermat's theorem. It's a bit more involved, so I'll just use Euler's theorem. You get the same result. I might do another video on Fermat later, but for now, let's focus on Euler's theorem because it's a bit easier to show. So really what we want to show, and that's exactly what they show in section 6 of the paper, is to show that the decryption of an encrypted message using RSA will lead into the original message M, obviously mod n. Everything here is mod n when it comes to encryption and decryption, at least. Okay, so first we start expanding these two functions here, the decryption and the encryption functions. So if I were to expand the decryption first, that means that that entire thing here is raised to the power of the private key. We denote the private key as D. That is very common in RSA. And then we can expand the inside, right? So what is the encryption of M? Well, that is raising M to the power of the public key, E. Okay, so that gives us M to the power of D to the power of D. So that is basically M to the power of E times D. All right, mod N. Now, we have to look at the definition of ED. Like, how do we choose the two keys or the key pair, right? There is a relationship between the private key and the public key. And the relationship is that if we multiply E and D, we should get 1 mod phi of n. So we know that these keys exist in a different group, which is the, it's not this group, Z of n, rather it is this group, which is a secret group. So phi of n should not be known to the adversary. N is known because n is a public key. So the public key, in RSA is two parts, the modulus n and the public exponent e. So this relationship is true because we know that d is the inverse of e in phi of n, right? So this is why we're able to say or to write that e times d is congruent to 1 mod phi of n. So we have this relationship and we want to use it to continue with this proof. All right. So now we rewrite this as this, right? So we replace ed by 1 mod phi of n. So that's what's going to be in my exponent. Okay. Now, there's a common mistake here. Some people think, well, I'm raising m to the power of 1, so I can just get rid of this and I get my result, which is m mod n. But that's a big mistake because we cannot just ignore a modular term in the exponent. A modular term in the exponent is as important as a modular term down here. Okay, so we cannot just get rid of that. We have to do something about it. All right, so I can rewrite 1 mod phi of n as follows. Remember, 1 is really the remainder, right? So I can write it as 1 plus, and then I can write this as k phi of n. So k is some multiplier of phi of n. It could be anything, it doesn't matter. So now we have m to the power of 1 plus k phi of n mod n. Okay, so here I'm going to do some arithmetic to the exponent. So this is, some tricks of exponentiation we also be familiar with. So I can rewrite m to the power of 1 plus k phi of n as m times m k to the phi of n. We know that the plus in exponent, if we bring it down, it'll be a multiplication. Obviously, it has to be, m has to be the same here, right? So it's m times m to k phi of n. Then again, I can do another trick, right? Which is basically rewrite the multiplication here as a power. That's also true for exponentiation, right? So m to the power of k phi of n is m to the power of phi of n to the power of k. All right, so here's where the Euler's theorem will be used. All right, now let's also reflect a bit on Euler's theorem. What is it really? So if we look at the components of this theorem, we see first of all m is a message, but also it's any integer, right? In our case also, I mean, in asymmetric cryptography we use integers, but they also could be binary strings, right? So m is an element of that group, z of n, right? And it's raised to the power of phi of n. So phi of n is Euler's function, and it's nothing but a count of how many elements we have in z of n. But it's not just all the elements, it's basically the elements that are relatively prime to n. So that's what phi of n is. Now if we raise m to the power of phi of n, we get 1, which is very nice, right? 1 mod of n. Now, in order for this to be true, first of all, focus on these terms. This is phi of n, this is n, right? So they have to be matching, right? So this phi of n is on this n here. Also, m has to be relatively prime to n for this theorem to hold, right? So now with that in mind, let's come back here, and now we're gonna do this replacement. So m phi of n mod n, right, is 1. So we can rewrite this whole term as 1. 1 to the power of k is 1. 1 times m is m mod n. You get your m mod n. That's exactly what we want to prove, because remember, we wanted to arrive to this. That's our, end goal here. So we have proven that the decryption of the encryption of M is equal to the original message M mod of N. And hence we have proven the correctness of RSA. And this will conclude our video for this time. Again, I hope this was useful. And again, the idea is that many times you read a paper, a cryptography paper, and you get stuck in one section. And I've looked up online, and there's not much related to explaining cryptography papers. All right, so I think it's kind of assumed that everybody will understand it, which is not the case. So I hope this is useful, and we'll see you next time. Thank you.